So we learned in 1A that the standard enthalpy change for a reaction, delta H for the reaction with this degree symbol, meaning standard, is the change in enthalpy for a process in which all the reactants and all the products are in their standard states. And in case we don't remember, standard state definitions are given here. For a gas, it's the pure gas at 1 atmosphere of pressure. For a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere, and the temperature of interest, which is generally 25 degrees Celsius. For a substance in solution, it is has a concentration of 1 molar. And so these are standard states. So like the standard enthalpy change, we can talk about a standard entropy change. Delta S with the degree symbol for the reaction, that's the change in entropy for the process when all the reactants and products are in their standard states. So like enthalpy, entropy is a state function, which means it only depends on where it started and where it ends up, not how it got there. Like a change in elevation, doesn't matter how you made that change in elevation, the difference in elevation is the same. So the change in entropy for this reaction is going to be the entropy of the products minus the entropy of the reactants. So we've talked about standard states, but now we need to define what standard molar entropies are. So this is the molar entropy of something in its standard state. So we had to decide what 0 was for enthalpy, because an absolute value, an absolute measure of enthalpy cannot be calculated. We don't know where 0 is, so we just decided. It's like with elevation. It's like, well, is 0 elevation, does that mean the exact center of the Earth? That's not very practical. What is it? And so we decided to use sea level, right, as 0 elevation. So for entropy, though, there is an absolute 0. And this brings up the third law of thermodynamics. The entropy of a perfect crystal at absolute 0 is 0. So here we have an illustration of a perfect crystal. There's no contaminants in it. There's no defects in it. At absolute 0, 0 Kelvin, all movement stops. There is 0 heat, right? 0 kinetic energy. All of those atoms are perfectly still. And then what I'd like to know is, does that mean the electrons are still as well? I don't know. We don't need to know that. So under these conditions, there's only one possible way to arrange the components. And so the number of possible states is 1. And based on Boltzmann's definition of entropy, S is equal to a constant times the natural log of W. Since W is 1, entropy is 0. So a perfect crystal at 0 Kelvin is 0 entropy. Any questions about that? Now, do we ever have a perfect crystal at 0 Kelvin? No, we don't. But that's where 0 is. And so we can measure from there. So here is a table from your textbook of standard molar entropy values for selected substances at room temperature. And we'll notice here, none of these are 0, right? When we looked at standard enthalpies and, standard enthalpies, a lot of them were zeros because elements in their standard states were defined as 0. So here, these are all positive numbers. There is a larger table in an appendix in the back matter of your textbook that has a whole bunch of other things in there as well. So at 25 Celsius, the standard entropy of the substance is dispersed into 1 mole of the substance. That's what we mean by standard molar entropy, the entropy of a mole. And so that's going to depend on the number of places to put the energy. So this is going to be affected by the state of the substance. Is it a solid, a liquid, a gas? What's its molar mass? What allotrope are we looking at? So an allotrope is a different form of the same thing. So carbon, graphite and diamond are both pure carbon, but they're different allotropes. They have very different properties. The molecular complexity and how much the solution is dissolved. Yep, question? Pardon me?
Can you define like allotrope, the word?
Yeah, so allotrope is like carbon. There's different forms of carbon. There's graphite and there's diamond. And they are both pure carbon, right? But they're not the same. And it has to do with how the atoms are connected to each other. Okay? Yes?
What does it mean by number of places per energy?
That's a good question. So earlier in this chapter, we talked about different microstates. And we had an illustration with the 2 flasks and 4 gas particles, right? And so we could have 2 particles in each side. That's one way to arrange the energies, one way to put the energies. Or we could have all 4 on one side, all 4 on the other side. Each particle is different, 1, 2, 3, and 4. So you could have 1 and 2 over here and 3 and 4 over there. Each of those different combinations is a place where we could put enemies, energy. It's a different arrangement that has the same energy. So when you have a more complex molecule, you're going to have more states, more ways that that thing can exist and have the same energy, or entropy, sorry. Does that help? Okay. So the more complicated something is, the more places to put the energy is, and so then the entropy is larger, because it can be more disorganized. So we learned that when you take a solid and melt it, the entropy increases. And so just in general, the entropy of a gas is larger than the entropy of a liquid, even if they are different things, just in general. So an entropy of a gas, more than liquid, more than solid. Because gases have more energy equivalent ways to arrange their components. They have more places to put the energy. So we see that water in the liquid state has a standard molar entropy of 70, whereas in the gas state it's 188.8. It's much larger. And we talked about how gases have rotational energy and translational energy, whereas a solid is just vibrating in place. And that has something to do with the higher entropy. Any questions? So molar mass affects standard molar entropies. So if we look at the noble gases, right? Helium, neon, argon, krypton, xenon. As they get larger, as their molar mass increases, the entropy also increases. The energy states associated with the motion of heavy atoms are more closely spaced, which allows for more dispersal of energy. So if that doesn't make any sense to you, don't worry about it. This trend of increasing molar mass results in increasing entropy only holds if these substances are in the same state. And they would also need to be somewhat similar to each other. So here we're comparing the noble gases that are all just atoms in the gas state. And we see that the entropy of xenon is larger, is the biggest. Here's the allotropes again. So this is an illustration of diamond, where we have carbon atoms covalently bonded to each other in 3 dimensions. And here's graphite, where we have layers. The carbon in each layer is covalently bonded, but then in between the layers, they're held together just by intermolecular forces. And that's why graphite is slippery. Good catch. Graphite is slippery because those layers can slide, because they're just held together by intermolecular forces, which are very weak. So the graphite is less constrained. It can move more, has different options, and so the graphite has a higher entropy than the diamond does. Any questions? So if we're looking at a particular state of matter, like liquids, the entropy will generally increase as you look at increasing molecular complexity. So let's look at the possible types of motion for kinetic energy. We have translational motion, which is this molecule moving through space. We have rotational motion, things spinning around in one place. And then we also have vibrational motion, where those bonds can stretch and contract and stretch and contract. So if you have more bonds, then you've got more possible vibrational modes, and so then you're going to have higher entropy. So if we compare argon and nitrogen monoxide, argon has translational motion and rotational motion. It can't do vibrational motion because it doesn't have any bonds. There are no bonds to stretch. NO has one bond, and so that bond can stretch and constrict. And so the entropy of NO is going to be higher than the entropy of argon. Here we're comparing two things that are almost identical in molar mass, right? And they're also in the same state. Any questions? Looking at carbon monoxide and ethene, C2H4, nearly the same mass, right? 28.01 and 28.05, like super, super close. But C2H4 is more complicated, it's more complex. We can draw a Lewis structure. So carbon monoxide, yeah, I think that's right. Or C2H4. Here there's one bond, and here there's 5 different bonds. This is more complicated. It can be more disordered because there's more places to arrange it when it has the same energy. So if you think of a child's bedroom, and this child has 2 toys, right? So, they could both be on the floor, they could both be put on the shelf, one on the shelf, one on the floor. There's a limited number of ways you could arrange things. But what if there's 10 toys? Now there's all kinds of different combinations, right? Things can be messier. There's more ways to arrange them, and so that's more entropy. Any questions? If you have molar mass and complexity both increasing, then entropy will also increase. So here we have nitrogen-oxygen compounds. They're getting more complicated, and their molar mass is also getting larger, and so the entropy is increasing. The extent of dissolution. So if you take a crystalline solid and you dissolve it in solution, that will generally increase the entropy, because now it's going from a crystal where everything was arranged in a particular way and was fixed there. And when it dissolves, now those ions are able to move away from each other, and there's lots of different possible arrangements of those ions that are going to have the same energy. So potassium chlorate in the solid state has an entropy of 143, but when it's dissolved in water, it's 265, so it's much higher. The energy that was concentrated in the crystal now gets dispersed through the entire solution. That's another way to think about it. Okay, any questions? So to calculate the standard molar entropy, we're going to use the same process we did for enthalpy. We're going to add up the entropy for the products, and we're going to subtract the entropy for the reactants. So the delta, final minus initial. So the final is the reactants. We're gonna, okay, all the reactants, what's their total entropy, and we're gonna subtract the reactants, and that's gonna give us the change in entropy for that reaction. So written in the form of a mathematical equation, it looks like this, where these giant sigmas are the sum of. N is the coefficient on each of the products. The coefficient represents the number of moles, and so you would multiply the standard molar entropy by the number of moles, add them all up, and then subtract all the reactants. Important difference here, when we're doing enthalpies, some of the enthalpies are zero, right? If it's an element in its standard state, the standard enthalpy is zero because that's what we defined as zero. But standard entropies are always non-zero at 25 degrees Celsius because they're only zero at 0 Kelvin and not even always then. Okay, so how do we do that? Let's calculate the change in entropy for this balanced equation. So we're going to look at the entropy of the products, and we're going to subtract the entropy of the reactants. So delta S, 0, for the reaction is going to equal, well, let's see. Look at the products first. In this balanced chemical equation, there's 2 moles of water, right? So times the entropy of water. This is in the gas state. This is in the gas state. It's important that you match everything up. So that's 188.8 joules per mole Kelvin. Joules per mole Kelvin. Okay, so when we multiply that, the moles go away. And the other thing we have over here is we have 2 moles of SO2 in the gas state. So we're going to look up SO2, 248.2 joules per mole Kelvin. And the moles cancel out. So that's the products. And then we're going to subtract the reactants. So reactants, 2 H2S. So 2 moles of that, and H2S in the gas state, 205.8 joules per mole Kelvin. Moles cancel out. Plus what happened? So, sorry, that was a 3. 3 moles of O2. Each mole of O2 in the gas state has an entropy of 205.2 joules per Kelvin. Again, the moles cancel out. So now we've got some math to do. 2 times 188.8 plus 2 times 248.2. And then we're going to subtract the quantity, 2 times 205.8 plus 3 times 205.2. And I'm getting minus 153.2. That would be joules per Kelvin. Any questions? So the change in entropy is negative. If we didn't have this information and we were just looking at this chemical equation, would we predict that the entropy was increasing or decreasing? Decreasing, because you can predict that by the number of moles of gases. All of these are gases. This is starting with 5 moles of gas and going to 4 moles of gas. That's fewer particles. It's going to be less disordered. It's going to have lower entropy. Any questions?